don't see anything there. Or is it just a picture?
No, it's empty. Okay, so good evening and welcome to today's very interesting asset colloquium by Professor Timothy Palmer, Department of Physics, University of Oxford. He's going to talk. I mean, you can guess from a very interesting title that he chose, a CERN for climate change, and he would like to argue that it requires a lot more international effort to kind of work on this important aspect, just like CERN being, let us say, the world lab for high energy physics. So to just say a couple of words in case you are someone outside the TF or family, ASSET stands for Advances in Science, Engineering and Technology. This is a forum which organizes colloquia at this time, that is 4 p.m. IST on every Friday on various matters of general interest, besides also dealing with topics of science interest in terms of instrumentation, detectors, electronics, and other related fields, including medical technologies and so on. And today I would like to particularly thank Professor Vivek Datar, the former project director, INO, and also Professor Subir Sarkar from the University of Oxford for proposing team for this particular talk. So I'm also requesting Professor Vivek Datar to formally introduce today's speaker.
Okay, thank you, Satya. Of course, it's a great pleasure to have Professor Timothy Palmer, who agreed to give this talk. Of course, this area is now really, I mean, it has been of interest for the last several years, but it has come into focus as a result, I think, of this Nobel Prize that was given this year. So let me say a few words about Professor Palmer. He is a Royal Society Millennium Research Professor in the Climate Physics at the University of Oxford. He is also the co-director of the Oxford Martin Program on Modeling and Predicting Climate and a professorial fellow of the Jesus College. He was a visiting scientist at the University of Washington, a Rothschild Distinguished Visiting Professor at the Isaac Newton Institute at the University of Cambridge. Interestingly, his DPhil was in the area of the general theory of relativity in Oxford in the mid-70s. He, of course, changed his field to weather and climate dynamics and prediction. And then he was first at the UK Met Office, then at the European Centre for Medium Range Weather Forecasting. He has had several honors bestowed on him. He was a fellow of the elected fellow of the Royal Society in 2003. He was a member of the Royal Society Council 2008-2009, president of the Royal Meteorological Society 2011-12. He has won top prizes of the American and European Meteorological Societies. He's a winner of the Dirac Gold Medal of the IOP UK. And recently, in 2020, he was elected an international member of the US National Academy of Sciences. He has wide interests. For instance, he's interested in, of course, the topic that he did his DPhil on gravitation, but also on the foundations of quantum mechanics, nonlinear dynamical systems, and so on. And his other interests, of course, include playing the guitar, playing golf, and then riding a mountain bike, it says in his website, in the West Berkshire Downs, which must be a beautiful countryside. So with these few words, I now request Tim to give his talk.
Okay, thank you very much for that very kind introduction. And I'll just share my screen. And can I just ask, is that showing okay?
Yeah, perfect.
Yes.
Okay,
Perfect.
great. That's fantastic. Yeah, so maybe I'll just start by saying how much my community of climate modelers, climate physicists, were by the award of the Nobel Prize this year to Suki Manabe from Princeton and Klaus Hasselmann from the Max Planck Institute. And it recognizes, that climate change really is part of physics. And indeed, the models that I will talk about today try to combine the quantum mechanics of how photons from the sun are absorbed and then re-radiated and scattered in the atmosphere. They describe the fluid dynamics of the atmosphere and the oceans using the Navier-Stokes equations. And they describe the thermodynamics of the atmosphere as an efficient thermodynamic system. So the core of climate models is very much based on the fundamental principles of physics. So it was a great, I think, honor for us to have that prize recognizing the importance of climate modeling in physics itself. But the main message I want to give today is that I think we still actually have a long way to go in producing climate models that really are good enough for advising governments and businesses and indeed individuals about climate change and about how to most effectively mitigate climate change and indeed, importantly, adapt to climate change. Certainly one of the big, I think, successes of the COP meeting in Glasgow was bringing the adaptation policy really up the agenda and treating it as almost, let's say, as important as mitigation. It's perhaps not as important, but it's extremely important. How does society around the world become more resilient to the changing climate that we will experience over the coming century? And I'm going to argue that we need to come together as an international community. And I'm going to propose a kind of a CERN concept for climate change modeling, that we need to come together internationally and develop a new generation of climate models with unprecedented levels of accuracy and reliability. And making use of the next generation, we're about to see this any day now really, of exascale, so 10 to the 18 floating point operations per second, dedicated exascale computing. And I would, just as if you're listening to this talk, just think all the way through. I believe very much that India can play an absolutely vital role in this, what I would say is a revolution that we need in climate modeling. So please bear that in mind as I talk. India really has a major role to play in this area if it should so wish. Oops, let me just, okay, so like I guess many areas in science, I mean, models are important, mathematical models are important, but often we have a hierarchy. We use a hierarchy of models, simple models for conceptual understanding, and complex models when we want really quantitative answers. And I just give some examples of a simple model. So these are three coupled differential equations which the meteorologist Ed Lorentz discovered in 1963. And these really were the prototype models that generated the phenomenon that we now call chaos. The figure there is the so-called fractal or strange attractor that you get by running the model over a long period of time from an arbitrary initial condition. And I'll show in a second, some insights one can get about about climate just from something as simple as that, three coupled differential equations. On the other hand, at the other end of the spectrum, we have complex models. And as I mentioned just now, the Navier-Stokes equations are very central to the fluid dynamics of the atmosphere and the oceans. And these, of course, are easy to write down as partial differential equations, but exceptionally difficult to solve computationally, because they unpack into literally billions and billions of individual equations describing all of the, indeed trillions of equations, describing all of the scales of motion in a turbulent fluid system. And in the case of the atmosphere or the oceans, from the very largest planetary scales right down to, microscopic scales. These are all coupled together by the nonlinear advection term in the Navier-Stokes equations. And then we need the largest possible computers to solve those equations. Let me just give a couple of examples of kind of insights you can get just by looking at something as simple as a Lorentz equation. So here on the top left are the Lorentz equations, and I've added an extra, what I would call a forcing term, to the equations, in addition, if you like, to the original equation. So this could very crudely represent the effect of, it could represent a change in the sun, or it could represent a change in the atmospheric concentration of, say, greenhouse gases. But it's kind of too simple in a way to be specific about what the forcing is. But how does a nonlinear system respond to adding an extra forcing? So what I've shown here is a two-dimensional plot of the three-dimensional state space of the model, and it shows the fact that the model has two regimes. So these contours they're essentially probability distributions, or they show the frequency of occurrence of a state as it oscillates around the attractor in a particular point in phase space. So the two kind of lobes of the butterfly shape of the strange attractor generate these two probability density maxima. Now, in the unforced equations where f is 0, the two maxima are equal and they're identical. So it's a symmetric system without any forcing. But if you add this forcing term, what it does is it makes one regime more populated, more likely to occur, and the other regime less likely to occur. Now, one of the interesting properties of this system is that if you vary this parameter theta, which, if you like, controls the direction of the forcing in state space. Okay, I've got the four different diagrams show different directions, different values of theta. What you find is that the response doesn't, if you like, vary. The position of the regimes does not vary. It's just the frequency changes. So if you have a forcing pointing upwards, the regime doesn't move in the upwards direction. It just becomes either more or less likely. So this is telling us that if the atmosphere has regimes, has these kind of quasi-stationary regions in state space, which it certainly does, then it's absolutely vital that we model these accurately. And as one of the problems with current generation models is that actually there are many shortcomings in our ability to simulate quasi-stationary regimes. And incidentally, this, whether the temperature, the regional temperature, is warm or cold, depends very much on the structure of the regime. So this type of model can explain, in principle, how something like carbon dioxide increases in concentration could increase the probability of regimes which are actually locally produce cold weather. And there was a paper earlier this year setting out a case where the freezing temperatures that occurred in Texas earlier this year, which led to most of the electricity generators shutting down, might actually be a consequence of climate change, because it's increasing the likelihood of a particular weather regime, circulation regime, which is associated with very cold weather, specifically in the area of Texas. Here's another quite interesting application of the Lorentz model. So I've shown here a time series of the Lorentz model, and it shows this irregular oscillation between the two regimes, or the two lobes of the attractor, the two wings of the butterfly, if you like. And then what we've done is to add stochastic noise to the equations. And you might think that the stochastic noise, if you had a very linear picture about the world, you might think that the noise would just sort of wash out this structure and you just get a kind of more unimodal kind of Gaussian structure. But actually, certainly for certain amplitude ranges for the noise, this adding noise can actually stabilize the regimes, and you get very rapid transitions. And a lot of the work, I'd say a little bit about it, but a lot of the work that we're doing in my group is looking at the impact of stochasticity in climate models. And actually, in some sense, the problems with producing long-lived regimes, as this model shows, can be helped by having noise, actually adding explicitly noise into our climate models. So this is an example of something which was motivated by this very simple kind of model. Okay, but now I want to move to the other end of this spectrum of the hierarchy.
Can I ask a question, Tim?
Yes, yes.
Okay, what is the physical explanation of this sort of behavior?
Oh, well, okay. I don't want to get, I don't want to get too much into this. It's basically because the if you like, the transition, if you look at the attractor and look at the channel, if you like, in state space by which the Lorentz system makes a transition from one regime to the other, it's actually in an extremely narrow, small part of state space. It's in a very restricted region. So the stochasticity moves you, it takes you off that. It perturbs you away from that small region, and that stabilizes. Then the system stays in that original regime longer. So it makes it harder for it to make regime transitions, because the noise kind of is kicking you out of this very narrow region of state space where the transitions occur. That's kind of basically what it is.
Are you claiming that that is a better explanation of how climate behaves in some settings?
Well, okay. I mean, as I'll come on to show, when we truncate the equations, I'll come on to this a little bit more later, but when we truncate the equations on a computer, then we have to find some way of dealing with the scales that we neglect by the truncation. And traditionally, this has been done by deterministic bulk formulae called parametrizations. And what I'm arguing is that, or what I will be arguing is that by using stochastic parametrizations for the unresolved scales, one can actually get a more realistic representation of the original system. So one of the shortcomings of climate models is that they don't get these regimes, particularly long-lived regimes, very accurately. And adding noise actually is an area where basically going from deterministic to stochastic parametrizations is an area where we see an improvement in this in the frequency of these long-lived regimes, and that's kind of consistent with this Lorentz model picture. But I'll come on to that a bit later. Otherwise I'll run out of time. So I want to kind of just move to this second point because the comprehensive models, of course, are important as well, and they're important, in practice because they determine how rapidly we need to cut our carbon emissions. They determine how countries or regions should adapt to climate change. This is, by the way, non-trivial because, if you're talking about adaptation, one of the first questions is, are you likely to get hit by enhanced flooding and storminess on the one hand, or maybe by enhanced drought and heat wave on the other hand? So the types of adaptation that you might spend money on would be very different depending on that, which was more prevalent for your region. Then there's the whole question of what's sometimes called Plan B. We could, in principle, for example, spray aerosols into the stratosphere, which would reflect some of the sunlight back to space. But, we really wouldn't want to be certain that we're not doing anything unforeseen by that. And I often use the example of the monsoons. I mean, can we be sure that doing something like that would not radically affect the monsoon circulations? And if it did, then we would certainly think twice, I think, about ever embarking on that direction. Models are increasingly being used these days for what's called weather event attribution. When we have a severe event, can we say, was it caused by climate change? How much more likely was that event due to climate change? And of course, if you can really model climate accurately, then that is a great aid for understanding climate. Part of adaptation, by the way, I see part of adaptation as improving our early warning systems. And again, climate models are used for making predictions on timescales of days, weeks, months, seasons, and sometimes even decades ahead. So comprehensive climate models are extremely important in the way climate science interacts with society these days. And I think probably people know that one of the ways in which climate change science is promulgated around the world is through the Intergovernmental Panel on Climate Change, which released its 6th assessment report in 2021. And the bedrock of that report is the output from an ensemble of models from around the world. And a thing called the World Climate Research Programme, which is partly under the UN auspices, they kind of organize a kind of coordinated experimentation protocol for institutes around the world who have climate models to run their models with a very fixed kind of set of parameters and specific scenarios for how carbon dioxide will increase over the coming century. And as I've indicated, these days we have about 100 models from 50 institutes worldwide. They're usually kind of synthesized into a probability distribution. Now, it's commonly assumed that this this multi-model ensemble is both necessary and sufficient to represent and quantify the uncertainty in climate predictions. But I want to make the case here that that's really not the case. That's not the case at all. And I just give some examples. I mean, I just chose a couple of things pretty much at random here, but so for example, mitigation. I think most around the world realize that we're probably not going to hit 1.5 degrees, and that we will have to hope that if we could get back to 1.5 degrees, perhaps later in the century, by what's called negative emissions, and that could be planting lots of trees, or it could be developing technologies to suck CO2 out of the air. But one of the problems with that idea is this idea, or this concept of a tipping point. Are there kind of irreversible changes in the climate system that may happen in the coming few decades, let's say in the first half of this century? A good example, one that I know a certain amount about, is what's called the Meridional Overturning circulation. This is an oceanic circulation. It's actually much larger in extent that's shown in this diagram. It's pretty much a global circulation, but it is responsible for keeping the North Atlantic, let's say, much warmer than it might otherwise have been. And it also plays a role in some of the tropical, particularly the West African monsoon. And there is a concern that, and from a theoretical point of view, there are simple models which suggest that this is a nonlinear system which might actually have a tipping point. In other words, this would actually occur if the circulation is driven in part by the fact that the water in the Gulf Stream is quite salty, and diluting the saltiness could shut off the circulation. And this dilution of saltiness could occur, for example, by the melting of the ice sheets over Greenland, or enhanced rainfall. So we have simple models which show this potential of the Atlantic meridional overturning circulation to shut off. And if it shuts off, it will undergo a kind of hysteresis effect, whereby it won't turn on again just by reverting back to the same saltiness and rainfall as before. Now, the point about that is that if these and there are other tipping points to do with the Amazon, to do with the ice sheets, and so on. And, the point about that is that if we pass tipping points, then sucking CO2 back out of the air, the negative emissions would be totally ineffective. So it's really quite important to understand if these tipping points really are likely to occur or not in the coming decades. The problem is that this current generation of so-called CMIT models doesn't really show any evidence of these tipping points. On the other hand, this is a colleague of mine at Bristol University, Paul Valdez, who's tried to study these CMIT models in paleoclimate, and he's argued that abrupt changes, essentially tipping point type changes, which we can see in the paleoclimate record, are not replicated by the CMIT models when they're run in a kind of paleoclimate mode, when they're run in conditions relevant to conditions, millions of years ago. And he argues that the models are too stable. They don't show these kind of nonlinear types of instabilities. Now, I want to. So that's a question about mitigation. Something that perhaps is more relevant to adaptation is the local weather that we can expect in the coming years and decades. And 2021 has been a kind of an extraordinary year for extreme events. We had temperatures that I don't think anyone would have guessed would be possible in a place like Canada. So in British Columbia, I lived for a year in Seattle many years ago. The idea that Seattle would experience temperatures close to 50 degrees Celsius would be pretty much unthinkable. And yet, in part of British Columbia, north of Seattle, that's exactly what they had, 49.5 degrees Celsius. And then very shortly afterwards, there were these devastating floods in the Rhine Valley across parts of Belgium and Germany. This is just a couple, unfortunately, whose property was destroyed by this But a lot of climate scientists, and one very prominent climate scientist in the US is Michael Mann. He made the comment to CNN that the signal is emerging from the noise more quickly than the models predicted. The signal is now large enough that we see it in the daily weather, even though the models didn't see it coming. In other words, if you look at the models and look at somewhere like British Columbia, they don't predict you run them over the early 21st century with observed carbon dioxide amounts. They don't predict the existence of temperatures at 50 degrees in British Columbia, and they don't predict rainfall intensities of the extent that was seen in the Rhine Valley. They certainly have extremes, but they're more the model extremes are not nearly as extreme as observed. And actually, although I don't have it here, but just thinking about this now, I mean, in India, you had some pretty devastating extremes of rainfall a few years ago in the Kerala region. And again, models just are not able to simulate extremes that are that extreme. They're too conservative when it comes to simulating local weather. Although they do a good job, in getting the basic structures right, they can't get these extremes right. This year a lot of the media was focused around British Columbia and Europe, but Africa had some pretty bad extremes as well this year, 2021. I wrote a paper a couple of years ago with Bjorn Stevens, who's the director of the Max Planck Institute in Hamburg, where we said that there are problems with the CMIT models. And another way of highlighting some of these problems is to look at how well they simulate the recent climate of the 20th and early 21st centuries. We've taken three models. This is from the UK Met Office. This is the one of the two major US models, and this is the Max Planck model itself. And we've looked at what would be called the systematic error in the simulation of rainfall. This is for the summer, northern summer, June, July, August. So where it's blue, the models are too dry, and where it's red or brown, the models are, so the other way around. Where it's blue, the models are too wet, and where it's brown, the models are too dry compared to observations. So these are the systematic errors of the three, what you would say probably the three leading models in the world from three different continents. And then I want to compare that with, and we're plotting this on the same scale, the climate change signal. So putting in a scenario, in fact, a fairly strong scenario for carbon dioxide emissions. This is how much rainfall will change in the last decades of the 21st century, according to the model. And the point we want to make here is that if you look at the scale is the same. So the point we want to make here is that the amplitude of this climate change signal is, if anything, smaller than the bias is. You see, this is a rather smaller signal than the bias. So if we believe, like I showed in the beginning of the talk, that the climate system is nonlinear, I mean, the Navier-Stokes equations are nonlinear, we have to be concerned, I think, about the reliability of these projections when the models have these basic systematic biases. It's a little bit like, if you take that Lorentz model and you add some kind of a bias which actually does move the regimes or changes the structure of the regimes, then the way it responds to some imposed forcing will be erroneous because the regimes are biased in some way. So in a nonlinear system, when you have systematic errors which are comparable or larger than the signals you're trying to predict, this is actually not a good state of affairs to be in. So, you know, for you guys in India, you obviously want to know how's climate change is going to affect the summer monsoon. Well, you see, look here, the biases in these models are pretty big over the Indian Ocean, the West Pacific, and they're bigger typically than the signal of climate change. So I don't think at the moment we can have a great deal of confidence in our ability to make very clear statements about how climate change will affect the monsoon circulations. And that's clearly not a good situation to be in, I don't think. So I just want to say a little bit about models then. What are they? And I'll use the Navier-Stokes as a kind of example. I mean, we have equations that will be similar partial differential equations for temperature, for density. I mean, the temperature will be a sort of expression of the second law of thermodynamics, first and second laws of thermodynamics. The density would be a kind of mass conservation. Then we'd have other variables for water and chemicals, which describe some kind of continuity equation with sources and sinks on the right-hand side. But let's just focus on Navier-Stokes for momentum, just for the sake of just focusing on something. So partial differential equation, it's an infinite dimensional equation mathematically. So we can't solve infinite dimensional equations typically. So we have to truncate them to a set of finite difference equations. And where we put the truncation scale, how big the grid boxes are. Actually, in the case of the models I use, they're spherical harmonics. The basis functions are spherical harmonics. Most models have grid boxes, but the idea is the same. You have resolved scales on the left, you have unresolved scales on the right. Where you put this dividing line between what you can resolve and what's unresolved is basically a function of your computer, how big your computer is. There's no God-given truncation scale. There's no natural truncation scale to put in a model, and for reasons which I'll explain in a minute. So current climate models, the CMIT models, typically this is around 100 kilometers. So these grid boxes are around 100 kilometers. Some more than 100, a few a bit less than 100, but they're typically around 100 kilometers. So what that means is that all cloud systems are subgrid scale. They have to be what's called parametrized, so they're represented by simple formulae, motivated by statistical mechanics, as I'll come on to say in a minute. All the radiation, shortwave, long wave, so infrared, ultraviolet radiation is parameterized, but that's of course not a problem because photons are tiny. But perhaps more important things like turbulence in the lower atmosphere, that all has to be parameterized. How flow over individual mountains, which can excite what are called gravity waves, which can propagate up and deposit momentum in the upper atmosphere, that has to be parameterized. In the ocean, all these little eddies, which are important in shaping the things like the Gulf Stream and the Kuroshio in the Pacific, they have to be parameterized. So there's a lot of parameterized physics goes on the right-hand side. And in a typical climate model, something like 50% of the computational time is parameterized and 50% is unresolved. So as I say, the concept behind parameterization is typically taken from statistical mechanics. Think about molecular diffusion or molecular viscosity. So there you have a lot of molecules, you have Avogadro's number of molecules, and you kind of do a bulk average of all these small scale processes to come up with a viscosity or a diffusive formula. So in parameterization, we assume that there are lots of, for example, cloud systems within a grid box and try to come up with some bulk formula for these cloud systems. Problem is, the world doesn't work like that. If you actually look at satellite data, you typically don't see such a kind of such a micro-canonical ensemble. You see a whole spectrum of clouds with different shapes and, well, with different scales at least. And you might have one or two, for example, mesoscale, what are called mesoscale aggregated cloud systems, which dominate what goes on in a grid box. Well, why does that occur? It's really actually a property. Why do we get that sort of multi-scale system? It's really a property of the Navier-Stokes equations themselves. And this is, discussed in many textbooks on turbulence, this one by Maida and Bertozzi. If you have the basic idea is there's a kind of scale invariance. There's a scaling symmetry or scale invariance symmetry in the equations. It can be formulated like this, that if you have one solution, u of x and t, you can from that generate a whole one parameter family of solutions by this scaling law. And what this scaling means in practice is that the energy spectrum in the atmosphere, or indeed ocean actually as well, as a function of horizontal scale, has a power law, has this kind of power law structure. So it decreases, so we've got the logarithm of energy here, and the logarithm of horizontal wavelength here. And you see the energy is decreasing, but it's decreasing in this, linear in log space, so it's decreasing logarithmically. It has a somewhat steeper slope for large scales, and then it shallows to a shallower slope for small scales. Broadly speaking, it's believed that that reflects the role of the Earth's rotation. For these larger scales, the dynamics feel the rotation of the Earth and the effects of Coriolis forces and centrifugal forces. That affects the dynamics of large-scale weather systems. But as you get down to individual cloud systems on scales of 100 kilometers, they don't so much feel the rotation of the Earth, and the spectrum shallows. So the point is that there is no spectral gap here. So a truncation scale, if you had if it dropped off to zero and then you had another bump up here at very high wave numbers, then parametrization would work. But it isn't like that. You have this continuous power law structure. There's no scale separation between resolved scales and unresolved scales. And so the problem is then that the CMIP ensemble, in the CMIP ensemble with the 100 kilometer models, they all have different parametrization formulae. But none of them actually account for the fact that climatic processes at this sub 100 kilometer scale may not be parametrizable at all. So they all assume that some form or another of the subgrid parametrization is possible. So there's a kind of a class error, if you like, that is being made here, and it's not being represented well in our climate model ensembles. So what I'm saying here is it's not so much that we don't know what the correct parametrization formula is. It may be that such a concept really doesn't exist. So what to do? Now, I want to argue that there is actually a good reason to try to increase the resolution of our models quite substantially to around 1 kilometer, from 100 kilometers to 1 kilometer. Now that for sure won't completely solve this parametrization problem that I've talked about, but it will alleviate it considerably. And the reason is that 1 kilometer, these convective clouds that I spoke about can actually be resolved. You can actually start to produce them from the Navier-Stokes equations directly. Things like two other things which I spoke about, gravity waves over topography, they also can be resolved. So the momentum budget will be better represented. And in the ocean, these mesoscale eddies, which are crucially important for shaping the sub-gyre circulations, the gyre circulations in the ocean will be better represented directly. Yeah, I talked about two of the events in 2021. We also had flooding in China. We had flooding in New York. And these weren't predicted very well, even on the short few days timescale. They weren't well predicted. And this was a blog by one of the leading meteorologists in the United States. His name's Cliff Mass. He says everyone knows what to do to get these forecasts better. We need high resolution. He said 3 kilometers, okay, but certainly a lot better than 100 kilometers ensembles that can be carefully calibrated. Okay. Now, the other thing I want to point out here is that we do have the technical capability these days of running 1 kilometer models, because we're moving towards very close now. In fact, one could even argue that some of our leading supercomputers are, for low precision calculations, actually at exaflop floating point. So this is just something I picked up on the web. This is from a couple of years ago. Hewlett-Packard announcing it will deliver the world's fastest exascale computer for the US DOE National Nuclear Security Administration at a record speed of 2 exaflops. Named El Capitan, it's expected to be delivered in 2023 and will be managed by various labs in the US. Now, this is the kicker line I wanted to emphasize. The system will enable advanced simulation and modeling to support the US nuclear stockpile and ensure its reliability and security. Now, I don't have any comment to make about whether or not the nuclear stockpile needs an exascale computer to ensure its reliability and security. If they say it does, then that's okay with me. But it just seems to me that the climate problem is certainly as important as the question about the continuing to ensure the reliability of the nuclear stockpile. But currently, the way climate models are run, they have to share resources. So a country that submits a CMIP model to the IPCC would typically apply for time on a multi-purpose computer, in that country. The computer would be probably likely shared across the scientific community. So the PIs of the particular climate model in question would write a proposal to the computer center for a certain amount of time and storage and so on, and it might get that. So it would be a couple of percent, let's say, of a shared facility. And I don't think that's the way to go with a problem as serious and important as climate change. And I would suggest it's just as important as this issue about maintaining nuclear stockpiles, because climate change is going to be affecting everyone on the planet. And it bothers me that much of our understanding, much of our knowledge about future climate change is very, very blurred and very uncertain because of these systematic biases and errors in the models. So my belief is that 2 exaflops. A 2 exaflop machine needs to be dedicated to climate, and we can do it. I mean, this actually is we can run a 1 kilometer model today, but we just can't run it for many days because the computers aren't big enough. That's what it looks like. You're actually at the situation now where we're with 1 kilometer, where it's very hard to know actually whether one is looking at output from a model or from a satellite. There's a kind of a Turing test here. You remember Turing said, if you can't tell the difference, if you ask a computer questions and you can't tell whether the answers are coming from a computer or a human, that's a kind of a good test about whether the computer has reached a stage of intelligence. equivalent to a human, and of course, computers can't pass computers can't pass the Turing test for intelligence, but they're just beginning to pass, I would say, the Turing test for whether we can tell the difference between a model and a real satellite data. But the problem at the moment is we can't run these models long enough to use them for climate simulations. This is also, sorry, is that a question?
Yeah, very quick question. How difficult would it be to do something adaptive? 1 kilometer grids where you need them, 100 kilometer grids where it doesn't cause too much error. Is that very difficult to do? Or?
I would say it's impossible to do, because how do you know where you don't need the resolution? You see, I mean, it's not straightforward. Even in a region like, say, in the subtropics here, where you might think nothing much is happening, if you go up higher up into the atmosphere, maybe at the level where the lowest level of the atmosphere and the upper level, the stratosphere, occur, there are crucial processes going on at that interface, even in this sort of subtropical regions, which you need to get right. So my view is that there is no objective, although people talk about adaptive grids, but my own view is that certainly for the atmosphere, there is no objective way of determining which regions don't need resolution and which regions do need resolution.
I mean, as a function of time and circumstances, even that you're saying?
Yeah, I do. Yeah, no, So, and by the way, if you run a global model with an adaptive grid, you actually pay quite a penalty in terms of computational time for that adaptation. It's not a cost-free, if you like, option. So I think that combined with the fact that there is really no way, for example, in the extratropics, you need to get these vortices right. In the tropics, you need to get all these convective cloud systems right. It's really very hard to find a region of the world where you can say definitively that you don't need this higher resolution. So I think it's better just to treat it as a globally uniform high resolution model. I was going to say that in these are some snapshots of the ocean with different fields, if you like, in the ocean, again, modeled at 1 kilometer. It's conceivable in the ocean. It's just about conceivable in the ocean. One might be able to, there might be regions where you could say resolution is less important. So it's conceivable that in the ocean, there may be some advantage with adaptive grids. But for example, you certainly want to have high resolution in these boundary currents. This is the Gulf Stream. This is North America here. So getting high resolution in the Gulf Stream is important. And getting high resolution further up to the northeast, where the water sinks in these convective plumes, that drives the meridional overturning circulation. Those would be regions where you would need high resolution in the ocean. So conceivably, there's a role for adaptive grids in the ocean. I don't think there is one in the atmosphere, however. Okay, so I've been banging on about the need for a CERN for climate change for coming together for quite a few years now, I've met some sort of pushback. So I just want to talk about those a little bit. One pushback is that, well, if we have this CERN, we'll just be building one supermodel, and we'll be putting all our eggs in one basket. Having a diverse ensemble of models is a good idea. So, ergo, a CERN center is a bad idea. My own view is that I've never really thought of this CERN as just a single institute, and maybe this makes it a bit more kind of explicit. What I'm imagining here is actually some kind of federated center or federated institute, where each of these blobs, could, let's say, represent a continent. So we'd have North America, Europe, Asia. potentially other continents. Of course, it's not going to be quite as simple as that. For example, in Europe, we certainly have the UK and Max Planck, for example, and the European Centre for Medium Range Weather Forecasts are all working closely on producing 1 kilometer models. In the US, there are others. So it would be too crude to imagine a kind of one per continent concept, but a small number of a small number of federated centers. And the point about being federated is that they really would be working closely together to create, maybe, there certainly is the room for different flavors of these 1 kilometer models. The idea is each one would have its own dedicated exascale facility, and they would be working collaboratively to produce a kilometer scale multi-model ensemble at this level of detail, which would be impossible at the moment. The other objection is to say, well, okay, but there are still going to be processes to parameterize at sub 1 kilometer scale, some of the cloud microphysics, what goes on within, the tiny scale in clouds, or some of the boundary layer turbulence will still need to be parameterized. And that's actually where I would say that's where we can do better than we currently are with this stochastic parameterization. And I don't want to talk about that, but blurring out this error with some stochasticity is a good thing. I think what I'll do here is, rather than talk about that, just refer you to a paper in Nature Physics Reviews, that I wrote a couple of years ago on stochastic parameterization. Let's see, I'm conscious of the time, so I probably need to just really rush through the last couple of slides. I just want to say very, very quickly, we can actually do something to improve computational efficiency, because even with an exascale computer, we will need to think of ways of improving computational efficiency. One thing I've been working a lot on with my group is going from what's called double precision numerics, which is kind of default in scientific computations, down to half precision numerics. And with AI now, there are many computers where you can actually run your code with half precision and get basically a 4 times speed up. The problem is that sometimes half precision does not give good results. So these are some turbulence calculations we did. But there's a concept called stochastic rounding, which I could talk about maybe if there was a question, but I'll skip over. But which actually allows very good results with 16 bits. So I think there is some merit there. The other thing which I want to just mention very briefly is AI. I think, actually, I'm sorry, I'm going to skip over slides because I know the time is getting hard. But I think there's a role for AI for the parameterization process. So even the sub 1 kilometer needs to be parameterized. And I think we can use methods in neural nets to improve the computational efficiency of the sub 1 kilometer parameterizations. Okay, so I think I'm going to stop here. CERN. Oh, no, I have one more slide to make. So CERN, CERN has dedicated hardware, about $1 billion a year budget or more, actually. I mean, I think about $1 billion runs the Large Hadron Collider. I think with a similar sort of budget, we could have a few of these federated centers, each with their own dedicated exascale computing. Maybe an individual hub would cost around $250 million. So if we had 6 of them, it would be $1.5 billion a year. And importantly, this would be a meeting ground between climate modelers and the economists, the agronomists, the health scientists, the hydrologists, urban planners, social scientists, and other who would be, linking their models into the 1 kilometer models. I just want to say very briefly, I worked for many years at a place called the European Centre for Medium Range Weather Forecasts, which was a place where about 20, well, I think now up to 40 European and neighbouring countries pool their human and computing resources. And from day one, this place has been the leading meteorological forecast centre in the world. So it's a supreme example of what can be achieved if we pool our resources. So I'm just going to finish with, basically the summary, which is that, climate models have done well, and the model that Suki Manabe, who won the Nobel Prize, developed back in the 70s, showed us that climate change is a threat. But if we really want a sharp, detailed understanding at a level really needed for mitigation and particularly adaptation, I don't think the current models are good enough. I think we need to come together internationally and do this at a much more collaborative international scale. And I hope, India could play a role here. Maybe India could be one of the hubs that I talked about. So I'll stop there, and if there are any questions, I'm happy to take them. Thank you.
Thanks, Tim. That's a fantastic proposition. CERN-like institute or establishment for climate science. I hope we will have that one day a reality. There are already quite a few questions, and I think there will be more, I'm sure. Yes, there are more of them coming up. So let me start with Shravan.
Hi, I wanted to hear a little bit more about stochastic rounding. So you're using the numerical forward solver that's a finite difference or something like that in tandem with a neural net. Is that correct? Or
well, sorry, let me just go back. It's sort of independent of the AI. Let me just give you. I had this very kind of simple example just to illustrate the concept. So imagine, you've got these numbers, and the shading. I've represented the shading with 3 bits. So I can go from black to white, or some intermediate, number of bits. Now, I could round that just to 1 bit. So with 1 bit, I just have black or white. So basically, everything here gets rounded to black, and everything here gets rounded to white. So now I've lost, 3 of the figures. The stochastic rounding says take a bit, and instead of rounding it to the nearest, which would be black, you round it in a probabilistic way. So you round it to black or white with a probability, and the probability. So when you're with at this level, the probability is close to 1, but not identical to 1. And when it's down here, it's close to 0, but not identical to 0. And in this simple example, you pick up some information. And it's a very similar idea in the model. When you're doing the rounding, you don't round to nearest deterministically, but you round to nearest in a probabilistic way. And I think the underlying idea is this, that for the reason I've tried to explain, there is a good sort of physical reason to think of the, particularly as you come close to the truncation scale, to think of the processes as not completely deterministic, but as partially stochastic. So introducing this stochastic rounding is kind of consistent with this notion that physically there is stochasticity in the system associated with subgrid scales. With 16 bits, you get all the benefit of being able to transmit data from one node to another node with far reduced, with a quarter of the precision that you would otherwise need. And of course, much of the energy these days in the computer is communication. So you're reducing the number of bits communicated by a factor of 4, will reduce energy consumption by a factor of 4. And that's the main determinant of computer speed these days. but keeping the stochasticity in the rounding gives you it means you don't it means you don't degrade your the accuracy of your simulation. This is all apropos of the idea, really, that in a nonlinear system, noise can be, as I said at the bottom, a positive resource. You shouldn't necessarily think of noise as something negative, as you do in linear systems. So I don't know if that helps a bit.
The errors cancel. Is that a fair way to think about this? Because it's noisy, both sides cancel and reduce the error.
Yes, if you like. So you're not. That's right. I mean, you're not always. Yes. Or another way. Another way of looking at it is like this. If you have. So imagine. A good example actually is, think of the for example, melting of permafrost, which is a very, very slow process. It's on timescales of decades. So you either need very, very, very high precision in your deterministic calculation so that at every time step you don't truncate the potential melting effect to zero from truncation. Or if you have it in this stochastic way, you can still so where you're not always truncating, for example, the tendency to zero, but there's a probability of truncating it to a non-zero number. You allow in a kind of stochastic way for this slow melting of permafrost to occur. So in a way, you're right. You allow for both, but it's a way of it's a kind of way of having your cake and eating it, to be honest. I should say, by the way, what I hope to do I've been trying to persuade the computer manufacturers that this stochastic rounding should be actually done in hardware rather than in software. That would improve even more the efficiency of these schemes. So I'm a great believer that in future years our supercomputers won't necessarily be completely deterministic machines. I think there's a lot of advantage in having stochastic supercomputers.
Okay, so Tim, we have quite a few questions.
Yeah.
So a couple of them on the YouTube, so we will get it going quickly. The Bridge, can you ask the next question?
Can I? Yes, please. Thanks a lot. So my question is mainly in climate sciences, I've been following up, and then you have a lot of different sources of data from different agencies, climate sciences, earth sciences, so on. I was wondering how standardized are those data sets? For example, if you're getting from CDO from NOAA or CDS from Europe or some Indian agencies provided, is that data standardized? I mean, if somebody wants to do run a model from these different agencies, how easy or difficult life is on that?
I think actually, because the data is used, typically used every day for weather forecasting, there's quite a lot of effort in ensuring that, the different types of data have compatible, if you're talking about sort of data formats, I think that, that is a problem that probably is reasonably well solved, that they have comparable types of formats so that a model can ingest data from completely different sources quite straightforwardly. I think actually there are still some issues with ocean data being slightly incompatible, but I mean, of all the problems, I don't think that would be the biggest one.
And more or less, the agencies are open enough for providing the data sets from the satellites and so on.
Yeah, indeed. I mean, that's one of the great things, I think, that for example, in Europe, we use data from NOAA and NASA, and I think we use a lot of Indian satellite data, Chinese, and so on. And I think, there's a kind of an international agreement, certainly in weather forecasting, that, the data is provided free of charge around the world, and then the forecast products, so we in Europe would provide forecast products free of charge to other countries and other continents. And there's the World Meteorological Organization, which is a UN organization, is responsible for ensuring, the free and open provision of data. There are some issues when it comes to, highly detailed data, which may have some commercial advantages and so on. But I think for much of the basic data, it's free and open. Yeah.
Okay.
Thanks.
May I ask one question?
Can we go to Professor Datta?
Okay. My questions are probably a little naive. Grid computing is used in, for instance, in the high energy physics field. Is that useful in the area of climate science? That's question one. The second question is, what is the effect of, let's say, solar, storms and things like that, or maybe volcanic eruptions, tectonics, on these models?
Just on the first question, what is important for running a model is, if you have 1 billion grid points, for example, it's crucial that the data from the grid points, so the calculations you do at the grid points, can be communicated, from one grid point to the neighboring grid point or the neighboring cluster of grid points, as rapidly as possible. Literally as rapidly as possible, because otherwise the computer just ends up waiting, for data to arrive before it can compute the next point. So if you have a kind of distributed network of computers where you just distribute these grid points, and they're literally in different parts of the world or something, the latency would just be unacceptable. You'd end up.
So it's not practical. Okay.
Yeah. So having a highly centralized supercomputer is still, I think, pretty important. Now, when I talk about these hubs, each hub would have its own exascale computer. Now, the hubs would only communicate at the end of the calculations, where the ensemble, you make probabilistic computations from the ensemble. So there, the latency issue wouldn't be important. So you'd have a kind of a if you like, a cloud of supercomputers, but each individual computer that's running a 1 kilometer model would have to be a very kind of would be based on highly localized, processing units. About the sun, certainly solar storms affect the upper atmosphere, and and potentially, they certainly affect the meteorology of the stratosphere and the mesosphere, and there are specialized models which have very, where the top of the model goes up to very, very high altitudes, and you have reasonably good resolution, vertical resolution in the high atmosphere. As far as climate change is concerned, I wouldn't personally treat that as a top priority. Volcanoes, yeah, for sure, volcanoes can affect the climate, and certainly a lot of the regional, the effects like what was called the Little Ice Age in Europe in the 18th century. That's believed to be the result of several big volcanoes erupting. Now, the problem there is that, it's impossible to predict a volcano erupting. So it is conceivable, it is conceivable if we had a lot of volcanoes going off, very big volcanoes, putting masses of aerosols into the stratosphere. That would do what these geoengineering proposals would do. It would create a blanket which would scatter sunlight back to space, and then that would have a cooling effect. But it's impossible to predict that. So you can't really put it into the models because we don't. I mean, if you talk to volcanologists, they still say we can't predict volcanoes at all, or earthquakes even. But of course, it's an important part of climatic research. I mean, a lot of people do work on the impacts of volcanic eruptions on climate, and again, I think that would be something where this 1 kilometer model would actually give us a lot of new insights and information.
Thank you.
Can I ask for my questions, please?
Okay, Sandeep.
Is there?
Yeah, so I'll go ahead and ask. Is that right?
Yeah.
I have just two quick questions. One is, of course, now you're seeking, I guess, 1 million times speed up by going from 100 kilometers to 1 kilometer grid size. In time scales also, are you looking for a speed up? Currently, what's the time scale at which you do computation? And would you like that to be also further shrunk?
Yeah, well, you mean the time step? The time step?
That's right, yeah.
Yeah, the time step is typically measured in minutes. So it could be 15, 20 minutes, something like that. And there is you always have to worry about computational instability, that if you increase your resolution, your spatial resolution, and you don't increase your time step, you're subject, you could be subject to numerical instability. On the other hand, there are sort of advanced time stepping schemes. They're called semi-Lagrangian, semi-implicit, which are actually quite stable to long time steps. So well, I think, my guess is that it will be necessary to reduce the time step, but it probably won't be in complete proportion to the reduction in the spatial resolution.
Very quick, one more question. Now, you mentioned these very popular models. I am new to this area. Would it be possible for me to get access to these models and play around with them and even contribute to changing them? Are we at that stage, or?
Sorry, I'm sort of hesitating because I know for example, if you were in the United States, the National Center for Atmospheric Research, one of its duties is to make available a climate model that can be run, by the entire academic community. And similarly in Europe, we have similar facilities. I would imagine, as somebody based in India, you probably could apply for and get access to these models. On the other hand, it would be good if there was something. To be honest, I'm not quite sure what the situation is in India, whether there's a similar kind of a community. I mean, these things are often called community climate models, where you can, run them on your local. I mean, some of them even have such low resolution you can run them on servers, university servers and things. Yeah, I mean, in principle, yes, but I'm not quite 100% sure, in your location what the options are. But I'd be happy to kind of explore that afterwards if you're interested.
Thanks, Ravata. Can we have your question?
Yeah, hi. Yeah, thanks for the nice talk. I have a couple of questions. My first question is a very basic question. What are the inputs or parameters required for climate modeling?
Oh, well, I mean, when you talk about parameters, you see these parameterizations. I mean, there are parameterizations for boundary layer turbulence. There are parameterizations for clouds, cloud microphysics, convective clouds. There are lots of different schemes. And they all have free parameters. So if you ask how many free parameters are there in a climate model, it's 100, at least 100, I would imagine. Hundreds probably is the answer. I mean, some of them are more crucial than others. And obviously, some of them are well known. I mean, you have to put in the gravitational constant as a parameter. And that's, of course, extremely well known. But on the other hand, you have to, for these convective clouds, you have to say, for example, how much air in a cloud, a kind of warm, moist air is diffused into the environment in a convective cloud. That's a very uncertain parameter. Or some of the, the structure of ice crystals, how the crystalline structure of ice crystals, is aligned with the motion in the cloud. I mean, these are just parameters which you put in, which, and that contributes to the albedo of the cloud, how much light is scattered, by a cloud. Those are very uncertain parameters. But in total, they're altogether, there may be 100 or more of these parameters. Now, then of course, there's another type of parameter, if you like, which is that if you do a climate run, you have to specify how rapidly carbon dioxide concentrations increase in the atmosphere in the model. So we don't have. I mean, that's not. That's a function of how humanity decides to tackle the climate change problem. So you have to put that in as an input. So that's an input. How rapidly are carbon, what are our carbon emissions going to be in the next 100 years? That's an input for a climate model. The brightness of the sun, the energy coming out from the sun is an input, which you have to put in. So there are kind of parameters which relate to the climate system itself, which have to be input, and some of them are very uncertain, and some of them, as I try to argue, they're not even well posed parameters. Actually, it's not like as if you can't actually go out and measure them because they're not particularly measurable, because the whole concept of a parameterization is problematic for some of these processes. And then, as I say, you have inputs, external inputs, which is like how our carbon emissions will evolve, and how the sun, will the sun stay as bright as it is now, that sort of thing.
Yeah, thanks. My second and final questions, last questions. How the temperature anomaly and climate change are related? Is there a strong relation between them?
Well, yeah, I mean, the basic idea is carbon dioxide is a greenhouse gas. The more emissions we emit into the atmosphere, the higher the carbon dioxide concentration will be. I mean, there are secondary feedbacks, of course, as carbon dioxide increases, so the water vapor concentration in the atmosphere increases, and that's a greenhouse gas. So the more emissions we put in, the larger the global temperature anomaly will be. Sorry, I didn't. Yeah, I don't know. Maybe I didn't talk very much about the basic climate science, but yeah, I mean that's well understood. You don't even need a climate model to tell you that. The more CO2 we put in the atmosphere, the warmer the planet will be. But it's not a simple linear function. That's the problem, because of these feedbacks. For example, we don't understand terribly well cloud feedbacks, how clouds will respond to increasing carbon dioxide concentrations. And clouds have the propensity to either damp or amplify the climate change signal, depending on how exactly clouds change. If low-level clouds start to dissipate and high-level clouds, very high-level clouds start to increase, that will actually amplify the climate change signal. That's the worst-case scenario for humanity, by the way, if clouds dissipate at low levels and increase at high levels. If it's the other way around, if low-level clouds increase and high-level clouds decrease, that will actually damp the climate change signal, which means that climate change may not be quite as bad as it could be. Unfortunately, most of the models, the CMIP models, suggest that clouds amplify the climate change signal, which is bad news. But again, I would say that's not something one can be 100% confident about for all the reasons I mentioned. So basically, yeah, the temperature increases as the carbon dioxide amount increases, but exactly how much it increases, there are still uncertainties there.
Thanks.
So yeah, thanks. We have two more questions. One in the YouTube. So I'm taking the LP.
Can I ask, please?
Yeah, please go ahead.
Respected professor, I have two questions. One is regarding grid computing. In my sitting room, grid computing installed for D0 experiment, and very high frequency, very high radiation, and it was giving very high noise. And I was sitting, three people were sitting, and the person who installed grid computing was Mr. P. Nagaraj, was protecting his ears by hearing aids. I was sitting in the center, I did not know this, and my ears, right ear is directly exposed, and machines were very close to me. So I lost my right ear hearing loss completely. Now it is 85 dB. Because of this, my left ear I started using heavy load on left ear. This also I lost it. This also it is 90 dB. Now both ears I lost. Now I am impaired patient. Okay. Now when I asked my colleague, he said I am using ear protection. He didn't give me. Later on, I asked my colleague, we'll go to our supervisor, Professor Nabake Mandal, asked him. Then he said he denied. Then I went and asked my professor, Professor Nabake Mandal, I will make a glass partition in the computing grid. He said, you go and sit in the corridor, I don't care about you, he said. Is it allowed?
Okay, I don't think I can make too much. I don't think I can make too much comment on this, but the times when I've been in a supercomputer center, it certainly is true that computers can be quite noisy. I guess because of some of the fans and it's not so much the chips, but the keeping them cool with fans. I mean, that makes a lot of noise. And if I was working in a computer center, I would certainly wear ear defenders. But no, this is not my field, so I can't really make too much comment.
Said you go and sit outside corridor, and my colleague who is conducting asset colloquium, Dr. Satyanarayana, is very much.
Can I please?
Second question.
Please ask something connected with the.
I lost my hearing aid because of computing air pollution. That is my second question. India wanted to start INO experiment with 40,000 RPCs. We are going to use pion gas, about 90% in each RPC, very huge amount of gas. So whether it will affect environment. We are going to build a mega project INO. In that we are going to use 40,000 resistor plate chambers. In that we are going to use pion gas, R134A. Whether it will affect the environment.
Well, look, again, you're talking about something which I think is not exactly my field, but it's clearly important for computing that especially for climate, that these computers are environmentally sound, and it means, for example, that the energy used to run a computer should come from renewable sources. That's why a lot of in Europe, for example, a lot of computers are now being located in Scandinavia because the air is cool, so they don't need to be cooled. The cooling is less, and also there's a lot of hydro and wind power. So yeah, I mean, it's important that whatever technology we use, it has to be environmentally sustainable. So I certainly agree with that.
You can see my both hearing aids I am using.
Yeah.
Very unfortunate. If it is in America, you will not allow this. But in India, everything is possible because there is no value for human beings in India.
Yeah, thanks, Reddy. Thanks, Reddy. I have one more question to take. The question is from last question, Tim. It is from YouTube. So I think you have partly answered it, but let me nevertheless ask. This is Abhinav Chaudhary. How quantum physics can help us to fight climate change, and do cosmic rays influence Earth's climate? So it's taking your talk a little further.
Well, I don't know exactly what the question means, but one project which I am working on with scientists at MIT is whether we can develop algorithms for solving nonlinear equations like like the Navier-Stokes equation or the Lorentz equations, actually, on a quantum computer. I mean, there's a lot of hype, I suppose. There's a lot of excitement. Maybe it's hype, I don't know. But there's a lot of excitement about quantum computing. And, that there's a question, can quantum computers be useful for climate research? So I actually have a project, and there's a paper on the archive where we develop a quantum algorithm for solving nonlinear differential equations. Perhaps it's not. It would take me too long, I think, to give you the details about that. But I think it's still work in progress. So I'm not. It's not obvious whether it will be or not. The problem with quantum computers is they're so completely different to classical computers. People who don't work in quantum probably don't realize that. They're just, completely and utterly different in the way in which these algorithms work. And the Schrödinger equation is a linear equation, so it's not even obvious a priori whether nonlinear types of problems can be solved at all. But there are ways of dealing with it. But we're not sure yet whether it really will scale well, and that's the crucial problem at the moment, both with the algorithms, the software, but actually also with hardware. We're not even sure with quantum computers whether they're going to scale. We'll really need millions of qubits before we're seriously in the game of being able to compete with a classical computer. We're a long way from that. So I wouldn't hold your breath about quantum computing, but it's an interesting academic question, at least.
I'm sorry, Tim. Actually, one of my colleagues reminded that, is there a question from AG66? Is it Alak? Do you have a question?
Thank you, Professor, for your kind answer.
I promise that will be the last question. It is already for you past noon. Alak, you have to unmute your mic.
Professor, many thanks.
Yeah, now it is. Now it is unmuted. Alak, please go ahead. We can't hear you. Is it possible for you to type the question?
Can't hear it.
I can't hear you.
No.
Okay. I guess I think that is Indranil. Indranil, can you at least sign through the camera to let us know if you can do it or not do it.
Maybe, yeah. Maybe you can email me the question and I could answer it.
I think that is better. I'm sorry for making you wait. It will only be 1 hour 40 minutes. You are on the. Actually, it's almost 2 hours. You are on the call. Thanks very much, team. I can't thank you enough for not only for such a detailed presentation, but you patiently took up every single question. And
well, I would just like to say in conclusion that you know, I hope that I mean, your institute is clearly a very important institute in India. So I hope you will bring this message to your leaders, you know, because ultimately it's a decision for your government to make about whether, you know, it wants to you know, invest in such a concept. So, you know, if you're dealing with civil servants or government ministers, please, I urge you to please make this argument that we need to step up our ambition in climate modeling. And you know, I know for a fact that, you know, there are many great Indian scientists, and you have the, you know, certainly these days capability to do this type of modeling. So please, you know, please pass that message on to your government.
Oh, yeah, sure. I think at least from on behalf of all of us here, I will definitely take this to the head of the institution. And I mean, some of them were there in the call now. I'm not sure, he probably left, including Sandeep and I think even Shravan. These people do work on models, but not necessarily just for the climate changes, but maybe there is a big synergy and overlap that can be really worked out. And at least from my side, I will definitely take this, your suggestion to the head of the institution. I have a slight suggestion, request, if you don't mind. The question is there now typed on the chat window. I'm sorry for this, keeping you wait. The question says, will the kilometer scale resolution help in weather attribution to climate change for cyclone events?
Oh, certainly. Yes, absolutely. Very much so. And again, you know, I would just emphasize that with the current 100-kilometer CMIT models, if you look at the strength of the winds in a tropical cyclone, you know, they would hardly blow over, you know, a house of cards, never mind a brick building. You know, they just don't have the right intensity. But we know in weather forecasting, because we do have 1-kilometer regional models, which are used to make short range, 1 to 2 day weather forecasts of tropical cyclones. And there the models do get the intensity more or less correct. So that's actually a case where we know that a 1-kilometer model will produce a much better representation of the wind strength associated with a tropical cyclone. And so, yeah, I mean, you know, trying to understand weather attribution, or just more generally, how much more likely intense cyclones will hit a particular region. This is where a 1-kilometer global climate model will be very, very valuable.
Okay, I think now we should really bring this to a close. So thanks once again, team, for such wonderful interaction. I would also like to thank Professor Vivek Datar and Subir Shakar for once again, you know, proposing this talk. And thanks all of you, the participants, who really brought this lively discussion, and a lot more could be discussed after the talk. Thanks once again, team. All the best.
All right.
Thank you, team, for an excellent talk.
Thank you.
Thank you. Thank you.
Thank you. Thank you.